Hello, fourth graders. I want us today to learn a lesson on symmetry, which is lesson 82 in your book, starting on page 547. Let's pray. Lord, we pray you'd bless this lesson, that it would be well understood, that it would be short and quick as possible, and you would be glorified. In Jesus' name, amen. All right, so first of all, we need to do our mental math, right? So go ahead and do A through H and the problem solving problem. Take about 5 minutes or so to do that. So pause this video and then come back to it and we will go over the answers quickly. Letter A, 38 plus 46, you should have had 84. B, 67 plus 24 is 91. C, 44 plus 28 is 72. D, 3 times 50 times 10 is 1,500. E, I'll just give you the answer to that one. It should have been 4 or 9. And letter F, let's see, if the radius of a truck tire was 15 inches, the diameter would be 30 inches. Letter G, the answer is $3. Letter H, if you do all that math, the answer comes to 75. Problem solving activity. Some days I'm going to just let you do this whole mental math and problem solving on your own with help from your parents, but today's problem solving activity is really interesting and I think you need to see it, so I'm going to go over it with you. The problem says Landon is packing a lunch for the park. He will take 1 bottle of water, a sandwich, and some fruit. He will choose either a ham sandwich or a peanut butter and jelly sandwich. For the fruit, Landon will choose an apple, an orange, or a banana. Make a tree diagram to find the possible combinations of lunches that Landon can pack. Then list each possible combination. Hopefully, listening to this, you're thinking, we need to draw a diagram. A diagram would be the best way to list all these different fruits together. In fact, it's a particular diagram that we should use, a tree diagram. So let me show you what that looks like. Okay, so first of all, we see that Landon is going to have water. So let's write down water. Okay, no matter what Landon eats for lunch, he's going to have some water with it. Then we saw that there was 2 choices of sandwiches. So we're going to start with water, and we are going to write down the choices of sandwiches. So ham was one, and the other was peanut butter and jelly, PB and J. Okay. Now, for the fruit, Landon has 3 choices. So whether he has water with the ham sandwich or water with the peanut butter and jelly sandwich, he will have 3 choices. So our little tree is going to branch off and repeat those 3 choices both times. So he can have an apple, an orange, or a banana, all right, with the ham sandwich, or an apple, an orange, and a banana, I should say, with his peanut butter and jelly sandwich. So then it asked us to list each possible combination. So when we do that, we need a numbered list. So we could have water, follow the first tree pattern. Water with ham, with apple, or with an apple. That's combination number one. Number two is water with ham and, you guessed it, an orange. And an orange. And thirdly, Landon can have water with a ham sandwich and a banana. So far, just with the ham sandwich, there are 3 combinations, right? So then 4, 5, and 6 will be water again, this time with a peanut butter and jelly sandwich, PBJ, and an A for an apple. I think you're following along now. Water, peanut butter and jelly, and an O for an orange, right? And lastly, water, peanut butter and jelly sandwich, and a banana. Do you see any other possible combinations? I don't think you do. I certainly do not. So that is how we get our 6 different combinations. And we answered all of that completely. Now, you should have by now, and if you haven't, I would like you to view the 2 videos that I put on RenWeb, which is now called Facts. And on RenWeb, so I want you to click on the first video and then watch that entirely. You'll learn about symmetry there, when things are symmetrical. And then a second video, also on symmetry, but a little bit of a different aspect of it. They're fun videos. It will take only, I think, 6 minutes and 3 minutes. So if you've already seen that, great. Then you are ready to continue on, with me now. So let me go ahead and get us started by erasing this, okay? And I want you to now read a new concept in your book on page 548 while I erase this board. I'll be right back. All right. So as you can see, we are learning a lot about symmetry today. And to get us started, I want to kind of go over the couple of new words that you may have learned today. One is reflective symmetry. Let's write that on our board here. Whoops, I almost used a Sharpie. Not a good idea on a whiteboard. Reflective symmetry. It's still a little bit wet. I'm not so sure. Looked funny, but no, that's correct. By the way, do you see who's back here with me? Here's Coco helping me, watching over me. And let me show you what I wanted to show you. So here I have this picture of a gorgeous butterfly. And you can see that this butterfly is split right down the middle. And what I want to show you about reflective symmetry is that when you take a mirror or a reflection of something, and let's say I cover up the right side of this butterfly, and then I show you the butterfly in the mirror, the other side of its reflection, you can see that it looks like it completes the butterfly, right? So that's called reflective symmetry. Whenever you can complete an image by holding a mirror right down the middle, that's what we call reflective symmetry. All right. And the line of symmetry is that spot. If you were looking at my face here, the line of symmetry, if I could draw a line right down the middle of my face, you would get the opposite side, the other eye, half of my nose, half of my eye, and you would see that my body has reflective symmetry. Not exactly the same, but you get that the same, you can kind of complete the face with that. So in today's lesson, the point is that there is a lot of symmetry in nature. God created a lot of symmetry throughout the world. And in math in particular, we see symmetry in lots of different shapes and geometry, in polygons, for example. You can find lots of symmetry, and we need to be able to work with symmetry and figure out what shapes have symmetry, what shapes do not have symmetry. And then there's another aspect of symmetry called rotational symmetry, which you should have seen a video on that already. And you can also look at example 2 in your book, where a square is taken and turned and turned and turned and turned, and you can see how many times it can turn. And when a shape turns and still has and goes back to looking like the exact same shape as it was at the very beginning, then and you can count how many times it shows up looking exactly the same. That is called rotational symmetry. And I trust that looking at those 2 videos, you got a really good sense of what rotational symmetry is. So that is why I put those on there, okay? So one thing that I'm not sure was 100% clear on that video was different lines of symmetry. So for example, if you have a square, you have a line of symmetry right through the center, right? If I was to cover up one side of the square, for example, might be kind of hard to see, but you can imagine that I would be able to see the other side. It has reflective symmetry, so you would see the other side of the square. It would like finish the picture. The mirror would finish the picture for you. But this doesn't only go one direction. You have another line of symmetry through this square right in this direction. So if you then were to turn this shape, let's say, and look at the line of symmetry, these 2 sides would look the same, okay? But then there's another way to do this, which is, here's another line of symmetry. If you take a look, this side with this corner triangle and this triangle are also symmetrical. So if I held a mirror here, this right through at a diagonal, this side and this side would be completed. Well, the other side would be completed by a mirror. And then it has one more line of symmetry going this way, where these 2 corners basically look identical. So how many lines of symmetry there were? 1, 2, 3, 4. So this particular square has 4 different lines of symmetry, which is one thing that you see in example number 1 in your book on page 548 to 549. So let's see. All right. I think that is about it. Let's go ahead and move on to, let's see. Let's go on to our lesson practice, letter A. Letter A, we see a figure that says, first the instruction, of course, copy each figure and draw the lines of symmetry if there are any. So let me erase this. And we have some sort of shape that almost looks like a crown. Okay, so we have this shape that looks kind of like this, like a part of a crown. And we are to copy that down on our paper and draw the lines of symmetry if there are any. And I would think that you could tell that if I was to draw a line of symmetry across it horizontally, the top and the bottom would not look the same, right? However, if I were to draw a line of symmetry right through the middle, the two sides, if my line was perfectly straight, are symmetrical. Okay, is there any other direction? If I were to draw it this direction, no line of symmetry any other way. So letter A has one line of symmetry. Now let's look at B. We have two lines, something like this, where this corner goes out further and the bottom left corner goes out further. And if you think about a line of symmetry, drawing a line of symmetry, if you were to do it straight up and down, that would not work. If you were to do it this direction, that would not work. This corner would show up here. There's no exact line of symmetry. So for this one, we say none. There's no reflective symmetry and no line that would make it exactly the same. Now, if you started to turn it, you'd get it back into this shape with some rotational symmetry, but not with reflective symmetry, which reflection, remember, is the mirror part. Letter C. There is this triangle in letter C, and this is an equilateral triangle. What you saw in the video that with the lady with the accent is she was putting these little markers here, which our book has not shown us to do just yet, I don't believe. And these show that these lines are equal. So you see the little equal sign looking bits there. And so if all of these are equal, and I'm going to erase my marks that prove that they are, if all of the different sides are equal, so it's an equilateral triangle, equal sides, equal angular triangle, equal angles, then we would have some lines of symmetry here. First of all, we would have one right down the middle. So please draw that. Right, and if you were to look now, remember I've said that these are perfectly equal. I did not take a ruler, I didn't measure it, so I'm claiming that they're equal, right? So if they are equal, then here is like the base line, you could see with the point up at the top. But if all of these are equal, then you would have another line of symmetry that cuts right through this line, right? And if you start with this corner, you would have another line of symmetry that cuts through this line right here. Okay, so there are 3 lines of symmetry for letter C. Let's go to the letter D. Letter D, we have a capital W, the shape. It's not a polygon, right? It's not a closed shape like the other 3 were. This particular one is just the letter W, and I think you will see that right down the middle there is a line of symmetry, and there is no other way that I could put a line where it would look exactly the same, whether top and bottom or this direction, would not work. Okay, so that's letters A through D. Letter D had just one line of symmetry, as you can see. And please go on to letter X. Letter X. I will tell you that there is more than one line of symmetry in letter X. Let's see if you can find it before I get to it. Okay. So the letter X in E. And you see that okay? I hope you can. letter X. In fact, I think I will switch colors. Those of you that love color, you can see one line of symmetry go this direction, and you should be able to notice that there's another line of symmetry that goes that direction. So for letter E, there are two lines of symmetry. And for letter Z, you will find that there are no lines of symmetry for letter Z. All right, letter G, it says, which figures A through F do not have rotational symmetry? Okay, so let's think about that first crown looking figure. Does that have rotational symmetry? Okay, if it were to turn, so here, let's take a look at it closer. Okay, so that's this shape here. Okay, if you were to think of this as the top of it, and we turn it, let's say this direction. Okay, so 90 degrees to the right. Does it look exactly like that? No, it does not. What if we keep going and we turn it to where the top here, that V shape, is now pointing upside down? Does it match? Could it sit right on top of the first shape and look exactly the same? No, it did not. Now let's take that V shape and turn it again to where it goes this direction. Could I take this shape and put it right on top of the first one and it would look exactly the same and cover it? Also does not. So the very first time that it would work is when you turn it right back the way it started, and that one doesn't count, because if the only time it works is when it's exactly the same, then that is not rotational symmetry. Okay, so letter A does not have rotational symmetry. What about letter B? If you were to turn that shape round and round, you would find that it does have rotational symmetry. Let's take a look at that one. All right. Let's see. Letter B. So we had that shape again, remember? All right, so if we think of it like, how about we call this, let me see, how would I best do that? How about maybe I will put an X right there, okay? And I'm going to remember that X is that obtuse angle, okay? So now my two long sides are I'm going to turn it around to where, let's see, kind of difficult to draw this one, so hold on a second. Let me think about how I would do this. I think I would go like that, and like that, and like that, and like that. And now the X has just turned to here. Okay, does this look exactly like that, and would it fit right over it? I would say it does not. And this just turned at a 90-degree angle, okay, to where the X used to be here, and now I flipped it on one direction over. All right, now let's continue that, and now let's make the X move to this direction by turning it this way. So here I'm thinking about this longer side, the side on the bottom. Here we go. It's kind of tricky, but now we're going to have the X move, I think, over here. Did I get that right? No, the X is here. The big opening is here. Okay, and we see that when we turned it on twice, we have, yes, we have rotational symmetry. Here is one. So good. So this one does have rotational symmetry. So B is okay. What about C? Does C, the triangle, have rotational symmetry? Sure, you could flip that triangle a few times and you would see the rotational symmetry over and over again. Okay, so the only one so far for letter G, which is the one that we're on right now, letter G, sorry, that's letter G, about the rotational symmetry. The only one that does not have rotational symmetry so far was letter B. A did have, let's see, no, I'm sorry. Letter A does not have rotational symmetry. Letter B, we just found up here, did have rotational symmetry. Yes, letter C does have rotational symmetry. But what about letter D, which is the W? Does the W have rotational symmetry? Well, let's try the W and see. Are you with me? You doing okay? So here is the W. Now, I'm going to think of the opening as the top, right? And now I'm going to turn the W 90 degrees over. Here's a 90-degree turn. Does it look exactly like that, where you could place that letter on top of the other one? No. Now I'm going to do the opening at the bottom. Okay, now it looks like an M, an upside down W. Could I put that right on top of the W? I cannot. And let's turn it one more time. How about turning it where it opens over here to the left? So first of all, this was 90-degree turn. This is now 180-degree turn, so the exact opposite, right? And then this is now another, so 180 plus another 90, which is 270. Think 90, so 9, 18, 27. Add the zeros at the end for these big numbers. And at 360, so 9, 18, 27, 36, you see those are the multiples of 9. We are right back to straight up. And so that was the only time that it looked exactly the same, which means we do not have rotational symmetry on the W, okay? The X, we do have rotational symmetry. We could turn the X, and the Z, we would have rotational symmetry on the Z. So let's try the Z and see if I'm right. Okay, so here is the Z, right? We're going to call the top of the Z the top. Okay, now I'm going to turn it 90 degrees. And here it is, the first turn to the right. Okay, so now this is the top of my Z. And then I'm going to turn it completely upside down, which is at 180 degrees. And look what just happened. Looks exactly the same. So does it have rotational symmetry? It does. And then I'm going to, so now, by the way, this is the so-called top, right? Now, so I went this way, now down. Now I'm going to go back the other direction where I turn my arm. And I'm back to it looking like an N, with this side being the top. This is at 270 degree at a 270 degree turn. And once I get to the 360 degree turn, I am back to Z. So you can see it had one order of rotational symmetry here and a second order of rotational symmetry there. So the answer to G is that only A and D have rotational symmetry. Okay. let's see, in letter H, we are to talk about reflective symmetry. And this one we'll just think about as you look through your book and I look at mine. Letter H, it says, which figures in A through F have reflective symmetry? A, if you held a mirror, like the butterfly thing, remember? If you held a mirror to that crown shape, you would have reflective symmetry. If you held a mirror to that letter B, which is that polygon with the bottom a little bit off, like almost a diamond shape if you looked at it on its side, so B, you would not have reflective symmetry. Letter C, you could cut that triangle right down the middle and you would have reflective symmetry. And letter D, you would have reflective symmetry right down on the W, just like this. You can see that. So if I put that mirror there, you could see the other side of it, hopefully. I'm holding that right. Letter X, yes, you do have reflective symmetry. And so the letter E was a yes, and the letter F, you do not have reflective symmetry with that letter Z, but we do have rotational symmetry twice. Okay, let's look at letter I. Which of these polygons have reflective symmetry? So take a look at letter A. Yes, that has reflective symmetry. Look at B. You can see if you drew a line right down the middle of on letter I, we're on letter I. Draw a line right down the middle. Yes, you do have reflective symmetry. Letter C does not have reflective symmetry, and letter D does not have reflective symmetry. So the answer to I was A and B. Okay, now let's go on to our star problems. Before I go on, let me just tell you, if you need a break, because we've just done about 30 minutes and we're going to go about another 30 minutes. So this would be a great time to push pause, go get some water, go to the bathroom, whatever, and then come right back, okay? This would be a great time for like a 10-minute brain break, okay? And I will see you soon if you're gonna take a break, and otherwise, I'm gonna go keep moving, okay? So while you get ready now for our written practice problems, I'm going to clean our board, and please start written practice problem number 2 on your paper. Okay, just 1 second. Let me get myself a little bit more comfortable even. Okay. You want to get comfortable for 30 minutes of math, but I am here for you, and you will not have to do the star problems by yourself because I am here to do them with you, and I'm so happy to be with you guys. Seriously, I'm finding out that it's fun to teach even when I'm teaching from home, but I miss you all so much. So it's much more fun in the classroom with you, but I still love to teach. So here we go. Number 2. Let's look at number 2. We are on lesson 82, page 551, and number 2. Which says, which of these letters does not have a line of symmetry? Let's draw all the letters neatly. T, N, V, and W. Okay. Now, can you see that the T has a line of symmetry right through here? Okay. Let's see. The N has no line of symmetry, so that is our answer. We believe the V does have a line of symmetry, and the W does have a line of symmetry. So the answer to number 2 is N. For letter A. This is letter A. Okay, now let's look at letter 2B. It says, which of these letters has rotational symmetry? Okay, so if you think about the letter T, and we can definitely draw them if you want to. T with the top here, T with the top at 90 degrees does not look the same. T upside down does not look the same. And T facing this way, again, does not look the same. So T does not have a line of, does not have rotational symmetry. Boom, that one is out. So let me erase that. Okay. How about the N? N. N facing now this way? No. Facing down? Yes. And then starting the N over here? No. And bringing it right back, of course, does. So B does have a line of symmetry. I'm sorry, the N does have a line of symmetry. What about the V? Did I say that wrong again? Oh, I hope you're laughing. What I meant to say was that N does have rotational symmetry. What about the V? Let's do the V upright, the V to the right, the V upside down, the V this way. There is no line of symmetry. There is no rotational symmetry until you turn it all the way back around again. So V is out. And let's look at the last one, the W. We already did this one. W, W, the let's see, the W upside down, the W from the left, and the W this way. So we can see that it never matches it exactly again until it's right back, 360-degree turn all the way back. And that does not count for having rotational symmetry. While it's rotating, does it look exactly the same, is what that means. So for number 2B, the answer was the letter N. Okay, moving on. Let's see what else. Now we get to number 3, which says write the formula for the area of a square. Okay, well, let's do it. The formula for the area of a square is the area equals the side squared. So we learned that long time ago. My book says way back in lesson 66. Then it says find the area of a square with sides that are 12 inches long. So that means that each side is 12 inches long. Okay, so this is when you have a perfect square, such as we have here. Let's see. So area is the side squared. So if you have, so then the area, the one side, if all the sides are the same, you can do this. You can use this formula. Instead of area is length times width, you can use area equals the side squared. So that means that the one side, the 12 is replacing that letter S, and it becomes 12 squared, which means that base number 12 is going to be multiplied 2 times. So that does not mean 12 times 2. It means 12, this factor of 12, this base number 12, multiplied by itself. So just, you're going to use that factor twice, right? So what is 12 times 12? We should all know that by now. You can look at your multiplication chart. It is 144, and since they were inches, oh, by the way, this was 12 inches times 12 inches, so 144, we can say inches, and there's 2 inches there, two markers for inches, two labels. So we are going to go inches times inches, which is inches squared. Okay, all right, and let's go on. Number 5. Are you doing okay? Let's see. Number 5 says segment YZ is how many millimeters long? Now here you are going to take a look. You're going to look at segment Y, which starts at 40, and all the way to segment Z, which is at 80, right? And 80 minus 40 is 40. And we are talking about millimeters here. So for letter A, the answer is 40 millimeters. Okay. Now it says segment YZ is how many centimeters long. Notice that it did not change which letter you're using. We are still talking about YZ. The only difference is instead of millimeters, now we're talking about centimeters. So you should remember that 1 centimeter is the same as 10 millimeters. Okay, so if we're talking about centimeters, this is 40 millimeters divided by 10, which is 4. Okay, so keep in mind, like if you're looking at a ruler, that little bit on a ruler that is as wide as your pinky is about 10 millimeters or 1 centimeter. So we're talking about 40 millimeters, which is like about that much as 4 of my fingers. And each one is about 1 centimeter. So there you go, 40 millimeters or 4 centimeters. Okay. Let's move on. Number 9. Let's go on to number 9. Number 9 says, Nikki cut a rectangular piece of paper along a diagonal to make 2 triangles. Okay. And what we're actually going to do is number 9A. You can do it if you like, but I have a note here to just skip that one. Take some time. I don't want to take too much time. Letter B. The question now is, are the triangles congruent? Are the 2 triangles exactly the same shape and size that are inside of that box? And 9B, yes, they are congruent. Let's see which one is next. Number 13, it says here, draw 2 rectangles that show that 1/5 equals 2/10. 1/5 equals 2/10. Okay, so we always want to start with 2 congruent rectangles, right? So here's one. You see that okay? All right, and here is the other. Trying to make them the exact same shape and size like you ought to be doing. And it says, first of all, we have 1/5. We're trying to prove that 1/5 equals 2/10, right? 1/5 equals 2/10. So we need to divide this box into 5 equal parts and this box into 10 equal parts, right? So let's try to be really careful. Maybe mark it at the top. 1, 2, 3, 4. Remember, to divide a box into 5, we need to make 4 tally marks. So we have 1, 2, 3. That 4th line is going to divide that last one, so we have 5. And we are talking about 1 shaded out of the 5 equal parts in this rectangle. Okay. Then we have 2/10 over here, which is exactly the double the amount of equal parts. So why don't we go ahead and do that again? 1, 2, 3, 4 equal lines. Go ahead and make those lines. Okay. And now, since we're not trying to get 5, we're trying to get 10, go ahead and divide each of those into 2 as neatly, carefully as you can. I'm a little wobbly with my marker here, but doing okay. And now we are going to shade 2 of these. So 1 and 2. And do you notice that 1/5 and 2/10 cover the same amount of area? So they are equivalent. We can call them equal and be telling the truth. Okay. Number 15 says, is the product of 2 prime numbers prime? Okay, so when you get questions like about prime and composite numbers, what I would like to see you do is to give an example or two. Prove it to yourself and to me by trying things. So the first thing I might try, let's see, is the product of 2 prime numbers prime. So what we might want to set this up kind of like something times something equals a prime number. That is what we are trying to find out. Okay. If prime times prime, is it still prime? Okay. And so let's think about what a prime number is for a second. Okay, a prime number is a number that only has 2 factors, and they are the number 1 and itself, right? So what is a prime number? How about we think about maybe the number 3? Okay, I can check to see if it's a prime number by trying to factor it out. 1 times 3 makes 3. 2 times 3 is already too big. 3 times 1, there's nothing else. So 3 is a prime number, right? Where is my red pen? It kind of lost it. Okay. So this is like, yes, that is a prime number. So 3, and then let's try another prime number. How about 5? Check to see if 5 is a prime number. 1 times 5 is 5. There's nothing, no other 2 products that will give you the same, no 2 other factors using 5 that will give you a 5 without having other like multiples, 5, 10, 15. So only way to get 5 is 1 times 5. So we can see that that is a prime, not a composite number, which is the opposite of prime. And we have 3 times 5, which is, we know, is 15. And then the question is, okay, we tried any 2 prime numbers. Is 15 a prime number? Well, let's try it. 15. I hope you're thinking, no, I can think of other factors that multiply to give us 15 as the product. But let's just go down the list. 1, 2, 3, 4, and so on until we start repeating ourselves, okay? 1 times 15 is 15. 2 times something make 15? No. But I know 3 times something makes 15. 3 times 5. How about 4 times? 5 times something. But I've already started repeating, which means that's everything until it repeats. 5 times 3. And then the next one, of course, will be 15 times 1, which is another repeat. So, is 15 a prime number? Nope. 15 is a composite number. It has more than 2 factors that can be multiplied together to make 15 as its product. So the answer to number 15 is no. And we could just leave it at that. The technical answer would be the product of 2 prime numbers can never be a prime number. If you try it with other numbers, you will see that you will not get another prime number. You will never get a prime number as a product. Okay? We won't take the time to do that. So number 16, we have 28 times 20. We're going to leave the zero, the hanging zero, off to the side. We could even put a line like this through it just to keep it separate. We know we're going to need that zero, and 2 times 8 is 16. 2 times 2 is 4, plus the 1 is 5. Okay, now we don't need that line there. Don't confuse it with a 1. The answer is 560. Okay, number 17. Do it over here to the side. 17, 13 times a different multiple of 10. This time it's 30. Let's leave the hanging O off to the side. We could even put a line just to keep it really clear and straight. And now it doesn't look so scary, does it? 3 times 3 and 3 times 1. 3 times 3 is 9. 3 times 1 is 3. And there you go. The answer is 390. Okay, what else do we have? Let's see. All right. Let's go on to number 27, please. All right. 27 says draw an obtuse triangle. Go ahead and try to do that, first of all. An obtuse triangle. Hopefully you remember that at least, so we have to have one corner, one vertex, we could say, that is open wider than 90 degrees. So for example, here with this wide open bit that comes not straight up but over to the side is an obtuse triangle. Okay, now let's see. That was letter A. Letter B wants us to describe the segments of the obtuse angle. Let's see. We can actually, we're going to skip that one. All right, if you want to know what that is, we would have talked about the fact that the segments do intersect. They do cross one another, we could say that. But since they never form a right angle, they are not perpendicular. Okay, so we can't say that they're parallel. We can't say that they're perpendicular when we describe the line segments, right? So that's why we're going to skip it. If you'd like to write that information down, more power to you. Good job. And let's go on. So that is number 27. And we are almost done with our lesson today. Let's go on to number 29. Okay. 29 says in polygon ABCD, which side, see what happens when you don't stop for a comma? You just read it and it doesn't make sense. So let me try that again. In polygon ABCD, which side appears to be parallel to side AD? Okay, here we have a polygon that looks something like this. We say it's a polygon because it's a flat, closed, completely closed shape. There's no openings. And it's a two-dimensional, so it's flat, closed shape. Let's see. It says, which side appears to be parallel to side AD? Okay, this is D. And I've told you before that usually when we draw a polygon, we go around it. And if you were to name something A, B, C, D, not A, B, C, D, or some other crossing of it. So as it usually is done, that's how they have it here in our book. And which is parallel, which means like the two L's in the word pair, parallel. It has those two L's exactly next to each other. They will never intersect. So never cross one another. The one that is parallel to AD is segment BC. And they wanted to know which side. They wanted us to call it a side. So we will call it side BC. Okay, the side BC is also segment BC. We could have written it that way, but since they asked which side, we're going to call it exactly what they asked us. Now, there's a part B. So part A was this. This is what you should go ahead and have highlighted and have a box around it. Of course, by the way, this could also have been called side CB, because it doesn't matter which letter you put first. Side AD is parallel to side CB or side BC. Okay, that's the point of that. Now there is a part B to number 29. So let us do that. It says classify the angles, not the sides, not anything but the angles. So let's think about every single angle. So we're going to put A, B, C, D, and because there's all these different angles, right? So in fact, I'm going to put the little symbol for an angle. Angle A, angle B, angle C, angle D. And what do you see as angle A? So what you're looking for here, is it obtuse, really wide? Is it a right angle, exactly 90 degrees? Or is it a cute little angle that we call an acute angle, right? So A, you can see, is open, pretty wide, so it is an obtuse angle. B is an acute angle, less, and I think I'll write these out now, acute angle. C, what do you think? Looks like an obtuse angle to me. And D looks like an acute angle again. Acute angle. Sorry, I'm not writing as neat as I can because I'm kind of in a funny position trying to teach from my living room. All right, so next we have number 30, and that will complete our lesson. So let's quickly get to that. Don't want to hold you up too long. Our math lessons should be roughly an hour a day, and for the lesson part, just like we have about an hour to an hour 15 minutes straight of math class at school. But I'm trying to keep us at about an hour per lesson. I know investigation 8 was longer, but the cool thing about that is you didn't have any homework after that except for maybe your facts, right? So let's see. Number 30, our last star problem says, this table shows the heights of several tall buildings. Make a bar graph to display the data or the data. Either way you say it is fine. So there's a building. Look at the building names: the Pinnacle, Interstate Tower, 2 Union Square, and 28 State Street. Where are these buildings? Well, the Pinnacle is in Chicago, and so on. We see 4 different cities: Chicago, Illinois, Charlotte, North Carolina, Seattle, Washington, and Boston, Massachusetts. Notice the abbreviations for those states. And how many stories high, that means how many levels. My home is a single floor, single level home. But the Pinnacle building in Chicago, Illinois is 48 stories high. Huge. So let us draw a bar graph. Okay, so let's get started with the x-axis this way, the y-axis this way. We know that at this point is the origin, 0, 0, and we typically put numbers at the side and words at the bottom, but that's fourth grade. You can make a bar graph so many different ways throughout life, and you actually do in offices and different type of research people do. They make bar graphs all the time. So you need to be able to read one. Okay, so first it's the pinnacle. So go ahead and label the pinnacle. Next, it's Interstate Tower. I'm just going to say Interstate Tower, like, in fact, I'm going to run out of room if I'm not careful. Interstate Tower. Then it is, I'm going to say 2 Union Square. If I was doing this for my business, I would definitely write out all of those words. And then I'm going to write 28 State Street. Okay, now you know what a bar graph looks like. It looks like a long chocolate bar, right? So we're going to get to use what's going to look like a building anyway here to draw our data on this bar graph. But what we need to look at next is in different numbers that are used. Okay, so we also should always name a graph. I don't think we did that on a different lesson we did together online like this, but this is buildings and this is heights. Heights, and we usually put the measurement of the height, which in this case is in stories over here, usually written sideways. And let's see, I see numbers, the smallest is 32, the largest is 56. So we want to go from 0 to about 60 to cover all of our data. How about we go by maybe tens? I think tens might work, or maybe even 20s to get us closer. Why don't we go with 20s? Be a little fancier. I'm going to go 20, 40, 60. All right, we could continue this, but obviously we won't need to. This is kind of a shortcut. Instead of going 10, 20, 30, we could have done 5, 10, 15. We could have just done 1, 2, 3, 4, 5, 6, 7, 8, all the way to 60. But too much work, right? So let's just go straight into 20 since our first data is like 32. So think about where the pinnacle would, let's see, which one has 32? No, let's start with the pinnacle at 48. Okay, so maybe we'll draw our little segments for what comes in between so we can see where the 50 would be, because the pinnacle goes right up to 48. So find the pinnacle, find where 48 would be, and draw a bar graph. Okay. A lot of times when you see bar graphs like this, you will have different colors for each bar that comes up. So you're welcome to do that. You can color one color, another color. I don't think I have quite that many colors, but I do have red. I think my markers are kind of falling all over the place, but I'll switch to another color just for fun. All right, so the Interstate Tower, the next one, has 32 stories. So let's find about where 30 would be and just go a little bit higher than 30 for our next bar. And that is 32. And keep in mind too that the whole point of making a bar graph is this so you can see information that you've collected very easily. Instead of having to just read like this whole long paragraph, our book put it first on a table for you, and now we're drawing our bar graphs. Just make it really easy to see. Well, which building's tallest? 2 Union Square is at 56. So let me switch us maybe to red this time. And we have 2 Union Square in Seattle, Washington, where it rains a ton. I know I sound like a weather person right now. Let's see, let's go up to about 50, not quite 60, but what would be 56, and then color it in neatly. Okay. And lastly, we'll switch back to black since I don't have any other, oh, wait, I do have blue. 28 State Street goes to, is 40 stories tall. So I'm going to try to go 40 and draw this here. I got a little bit close to my arrow there. Okay, so obviously now just looking at the data here, looking at the bar graph, we could answer some questions very easily. We are not asked any questions, but I could ask you, what is the tallest building? It's 2 Union Square. What's the shortest building? Inner Tower Building. Interstate Tower Building, excuse me, and so on. So we can do that. Now, of course, there's one other thing that a bar graph always has, which is a title. And this was called Tall Buildings in America. So go ahead and put that on your bar graph too. Make me proud. And that is the end of our lesson 82. Lesson 82. Good job, everybody. Now please go back and do your non-star problems, but take a break first. This is a lot, an hour, 6 minutes, and we are finished. But do take a break now and then jump back on your star problems today, please, if you can. And get some help on those, all right? Because they need to be right. I want you to know how to do it right. Talk to you guys later. I will see you again soon and look for tomorrow's video. Thanks so much. Bye-bye.